Good morning. We are going to just kind of look how to put all of what we've been doing together into graphing our rational function. So I'll walk you through the first problem. We did this, I think, in class yesterday for some of you. We talked about all of the different pieces of it, but we'll just review that again here real quickly. So to find the y-intercept, we take the original function and we plug in 0 for all of our x's. So what that will look like is 0 plus 4 over negative 4 times 0 plus 16, which ends up being 4 over 16, or 1/4. So we write our y-intercepts as an ordered pair. That would be 0, 1, 4. Horizontal asymptote, you take a look at the highest power of your x's in both the numerator and the denominator. And in both cases, we have the same highest power. So that means that we use the ratio of those numbers that are in front of those highest powers. Essentially, we're going to ignore the rest of this and just look at those numbers out in front. So that leaves us with a horizontal asymptote of y equals negative 1/4. Next up, we're going to factor our expression. So we can't really do anything to the numerator. We leave that as x plus 4. But in the denominator, we can factor out a negative 4 to make it x minus 4. Looking for any holes in the function, we try to find giant ones. Since there are no giant ones, we would say that there are no holes in this function. And then finally, we have the two things that we do with what's left. So the x-intercepts take whatever's in the numerator, set it equal to 0, and solve. And we get our x-intercept of negative 4. And then the vertical asymptotes take whatever's in the denominator, the factors, set them equal to 0, and solve. Now this has a little bit of an issue here. When we try to figure out what vertical asymptote we get from that guy, it doesn't make any sense. Negative 4 can never be equal to 0, so what we know is that that does not result in anything that we need to keep track of. But we do end up with a vertical asymptote of x equals 4. Now, when we start putting this all together, I'll go ahead and graph each of these pieces. So my y-intercept is the 0.014, which is like right about there. My horizontal asymptote is y equals negative 1/4. So I will graph a negative line, and I'm going to graph it as a dashed. I'm going to graph a horizontal line that's dashed. So y equals negative 1/4 is going to be, sorry, I need to select the right marker here, right about here. And that's actually probably a little bit more like 1/2. So it's really close to the y-axis. We don't have any holes in the function, so we don't need to worry about graphing a hole, but we do need to graph our x-intercept at negative 4, 0, which would be right here. And then finally, we have a vertical asymptote at x equals 4, which will be a vertical line. Now, when I start putting this all together, I need to find a way to connect the points so that they make sense. On the left side of my vertical asymptote, I see my x and y intercepts sort of making sense. When we start connecting the pieces, we need to keep them so that they stay close to the horizontal asymptote and that they don't cross any vertical asymptotes. So we talked about how the horizontal asymptotes influence our end behavior. So we're going to have something that looks like this. Now, as far as what happens in this region here, I don't really care, okay? I'm trying to get a sketch of this graph. I don't care about super details here. One thing that we do know is that rational functions do not like to live, and I use that in quotes, next to each other. So when we graph our second part of the curve, the part of the curve that's on the other side of the vertical asymptote, um, it can't be right next to the curve that we've already graphed, which means there's only one part of this curve left, or one part of this graphing area left that we can use. Now, again, I don't care about how detailed we are. What I do care is that we stay close to the horizontal asymptote and we do not cross the vertical asymptote. And so we end up with a function that looks something like this. You can use Desmos to check it, but this is going to be a pretty good estimation. Okay, let's try another one. So we now have a new function. Let's go through and find all of our pieces. So we'll start with our y-intercept. Again, that means we're going to put zeros in for all of our x's. So when I put zeros in for all of the x's, I get 3 times 0 squared minus 3 over 0 squared minus 0. Now what we end up with is negative 3 over 0. That is not 0. Remember, if we try to divide by 0, that's undefined. So if something is undefined, that means it's not going to be on our graph. So we could say there is no y-intercept for this function. All right, second, our horizontal asymptotes. Again, we look at our highest power in the numerator, which is 2, and our highest power of x in the denominator, which is also 2. Same highest powers, which means once again, we're going to look at the numbers in front or the coefficients of those highest powers. And that's going to determine our horizontal asymptote. So y equals 3 over 1, or you could just say y equals 3. Okay, next up, let's factor. I'm not going to spend a lot of time factoring this. I think that you should be able to do so pretty quickly. So I'll just kind of quickly factor it off to the side here. We'll have 3 and then x minus 1 times x plus 1, and then we'll have x as a GCF and then x minus 1. All right, so if you look closely, we do have a giant 1, and our giant 1 is going to determine where any holes in the functions are. So we have this giant 1 at x equals 1, or we make the factor that is creating the giant 1 equal to 0, and we get the x coordinate for the hole. And then like we talked about earlier this week or end of last week, once you get rid of that giant 1, whatever's left is what we plug that x coordinate that we just found into. So I'm going to plug x equals 1 into that expression. So what do we get when we plug x equals 1 into that expression? Well, we're going to have 3 times 1 plus 1 over 1, which ends up just being 6. So I get a hole in the function at 1, 6. We'll come back to that in just a few minutes. Okay, whatever's left will help us determine our x-intercepts and our vertical asymptotes. So x-intercepts takes whatever's in the numerator and sets those factors equal to 0. Well, once again, we end up with something that just doesn't make sense. When we set 3 equal to 0, that doesn't give us anything. But when we set x plus 1 equal to 0, we get x equals negative 1. So we get a hole in the function at, an x-intercept at negative 1, 0. And then finally, our vertical asymptotes. Vertical asymptotes come from whatever's left in the denominator, setting it equal to 0, which in this case is just x equals 0. So now we have all the information. We can start to sketch this graph. And remember, this is just a sketch, okay? So there is no y-intercept. We do have a horizontal asymptote at y equals 3. So we draw a horizontal line through y equals 3. We have a hole in the function at 1, 6. So I'm just going to sketch that on here as an open circle. I have an x-intercept at negative 1, 0. And then I have a vertical asymptote at x equals 0. So that's going to be right along the y-axis. Now, once again, I have a little bit of kind of, filling in the blanks to do here. So I'm going to use what I know, which is I have a point on either side of that vertical asymptote. That's going to help me determine what the graph looks like. So on the side where we have our x-intercept, I know that this graph is going to continue to follow along the vertical asymptote, and then it's going to stay really close to the horizontal asymptote as we go out towards negative infinity on the x-axis. And then notice our hole is not next to, in other words, it's not in this region of the graph. These don't make good next door neighbors, so they can't live right next door to each other. But it can live in a diagonal relationship to the other curve. So we end up with something that once again follows along the horizontal asymptote and does not cross the vertical asymptote. And that's as good as we're going to need to get for this. All right, one more. So one more, let's see. We've got x minus 3 over x squared plus 3x. First step, let's find our y-intercept. Plug in 0 for all of our x's. And that's going to give us 0 minus 3 over 0 squared minus 3 times 0. Once again, we get something like this, negative 3 over 0. And just like in the previous example, we know that when we get something undefined, that means that that thing does not exist on our graph. Next up, horizontal asymptote. Look at our highest powers. In the numerator is 1, in the denominator is 2, which means we have our highest power in the denominator of our fraction. Anytime this happens, it automatically means that your horizontal asymptote will be y equals 0. All right, then let's factor. So we have x minus 3 over x times x plus 3. We do not have any giant ones. Therefore, there are no holes in the function, which is kind of nice. We don't have to worry about finding any of the gaps in that function. X-intercepts. Those come from whatever's left in the numerator, set equal to 0. So x minus 3 set equal to 0. Solve that, we get x equals 3. So we have an x-intercept as a point at 3, 0. And then finally, we have any vertical asymptotes come from whatever's left in the denominator set equal to 0. So we would set x equal to 0, and we would set x plus 3 equal to 0. And we end up with two vertical asymptotes, x equals 0 and x equals negative 3. Okay, so let's put this all together. There's no y-intercept. There is a horizontal asymptote at y equals 0. That's just along your x-axis. No holes in the function. We do have an x-intercept at 3, 0. Now, some of you might be bothered by the fact that the horizontal asymptote has an x-intercept on it. We talked about that last week. It is okay for us to touch and go from the horizontal asymptote. The one thing that we can never do is cross through our vertical asymptotes. So these are x equals 0 and x equals negative 3. Now something interesting happens here. We don't have a lot to go on, and I have 3 areas of my graph because we have 2 vertical asymptotes. So you may need to be a little creative here. So what I'm going to do is start to maybe pick some points, I'll do it up here, that we can plug into the function to help me get a little more information about what's happening, because I just don't know. I just don't know what's going on. So maybe I pick something all the way to the left of my graph. So maybe something to the left of my x equals negative 3 vertical asymptote. So what if I plug in x equals negative 4 into my original function? Let's see what we get. So we're going to get negative 4 minus 3 over negative 4 squared plus 3 times negative 4. That's a lot going on there. Let's see what we end up with. So we have negative 7 over 16 minus, that'll be minus 12. So 16 minus 12 is 4. So we get a point where x is negative 4 and y is negative 7/4, which, I mean, that's about what, negative 1 3/4, negative 1.75. So now I have this point that I can sort of go from negative 4, negative 1.75. So that's going to be like right about here. Well, that definitely helps me start kind of putting this picture together, because I know that we could cross through the horizontal asymptote, but we're going to stay close to it. Our graph probably lives in this bottom portion of our coordinate plane at this point. So at least we have that. Okay, so now let's pick a point somewhere between our two vertical asymptotes. So somewhere in here. I like that -1 is in here, so maybe I try -1. So I'm sort of running out of room here. Let me do this down here. Plug in -1. So if x equals -1, we're going to have, scroll, zoom out a little bit here, -1 minus 3 over -1 squared plus 3 times -1. So let's see, that gives us -4, and then 1 squared, -1 squared is +1, minus 3, so 1 minus 3 is -2. So we get 2. So we get the point -1, 2. So that puts us like up here. Now we've talked about how they don't like to live next to each other. So you're not going to see me drawing something that, has my graphs living next to each other. So going like this through that point doesn't make a lot of sense. So probably what we're going to see is something that stays up above the horizontal asymptote and goes through that point. It's going to kind of look like a parabola. Now it's not truly a parabola because it's contained by those vertical asymptotes, but it could kind of look like a parabola type shape. Now the last thing we need to do is think about how do we draw in the last portion of our curve. Well, we've talked about how they don't like to live next to each other, so we're probably not going to do this, all right, because then you'd have these two living next to each other. So it's going to be somewhere in this area. Now it's going to stay close to this horizontal asymptote. It's going to momentarily go across that horizontal asymptote because you have that x-intercept there, but it's going to remain close to the horizontal asymptote. And then that's it. That's a pretty good sketch of that graph. We have all the important information that we have found first and then put on the graph. Okay, I'd like you to try some of this today. There will be a worksheet up, or not a worksheet, a Go Formative up for you to practice with by the end of the class period. All right, I'll see you tomorrow.